Okay, good morning, children. Now we are moving to the next topic of the chapter, alternating current, and this portion. Topic is about LC oscillation. What is this oscillation and what is LC oscillation? About oscillation we studied in +1, isn't it? Oscillation, it is the to and fro motion. It is known as the oscillation. Then what is this LC oscillation? L and C. We know what is this L and C stands for, isn't it? So the last classes we studied what is L and what is C. L stands for the inductance and C stands for the capacitance, which are the two devices in an electrical circuit, isn't it? Two components, capacitor and inductor, and its property, it is capacitance and inductance. So if you are having a parallel connection of this inductor and capacitor, it produces electrical oscillation. Okay, it is the electrical oscillations with a constant amplitude or frequency. Such oscillations are known as LC oscillation. It is called a LC oscillation. That is when a capacitor and inductor are connected parallelly. And what is this? The capacitor is fully charged. The capacitor is fully charged and it is connected across an inductor, an ideal inductor of negligible resistance. It produces electrical oscillations, and that electrical oscillation, it is having constant amplitude or frequency, and it will be undamped also. Such oscillations are known as LC oscillation, or it is the electromagnetic waves. Electromagnetic waves. LC oscillations, or it is the electromagnetic waves. Okay, electromagnetic waves. We heard about this electromagnetic waves, isn't it? We studied that the visible light, it is a part of the electromagnetic spectrum. So how can we produce this electromagnetic wave? We are producing it by using this LC circuit. So let us see how this is producing, this combination, this connection is producing the oscillation. Okay, so what is LC oscillation? We can say that when a charged capacitor is connected across an inductor of negligible resistance, it produces electrical oscillations. It produces electrical oscillations of constant frequency or amplitude. Okay, such oscillations are known as LC oscillation. So write down next question. What is an LC oscillation? What is LC oscillation? Okay. So first we go for the qualitative explanation for this LC oscillation. Okay, then we will go for the mathematical explanation. Then we will compare this LC oscillation, that's electrical oscillation, with the mechanical oscillation. So this is the LC circuit. Okay, it consists of an inductor of inductance L and a capacitor of capacitance C. And you know what is a capacitor. Capacitor is a device which stores charges. Okay, and it is having two plates, positive and negative plates. And this is our inductor of inductance L. Okay, so what is the first thing? First we are considering, initially we are considering the capacitor is a fully charged capacitor. Fully charged capacitor. So the charges stored, we can take it as Q0. That is the maximum amount of charge stored in this capacitor. Okay, so it's not started discharging, only the fully charged capacitor we just connected across an inductor of inductance L. So what is it? Here there is energy. Isn't it? Across the capacitor there is energy, and what is the energy stored across the capacitor? It is half Q square by C. Energy stored across a capacitor is half Q square by C. So here the energy is the electrical energy. So I am representing it by UE. Okay, E stands for the electrical energy. So here now the charge is maximum. So we can write there will be the maximum charge across the capacitor, and that is equal to half Q0 square by C, where C is the capacitance. Okay, where C is the capacitance. Then, and at that time, what is the condition of the inductor? Nothing is there. Okay. Then slowly what happened? The capacitor starts discharging. Okay. So, this is fully charged capacitor and here inductor is there, nothing is there. So, definitely we know charges starts flowing from higher concentration to lower concentration. So, what is it? This capacitor charge starts discharge through the inductor L. So, the charge starts flowing. So, law of charge, there will be current I. Okay, there will be current I. So, what happened? We know that the current, when current passes across a conductor through a conductor, around that there will be magnetic field. So, what happened to this inductor? The flux associated with this inductor starts what? Changing. So, there will be an induced EMF, there will be a back EMF produced across the inductor, and this energy starts storing in the inductor, isn't it? So, what will be the energy stored across the inductor? Energy stored across the inductor is half Li square, where L is the inductance and I is the current. Okay, that we studied last class. Energy stored in an inductor is half Li square. So, this current is slowly flowing through this inductor. So, what happened? From the energy, that is initially UB is equal to 0, and here it is the magnetic energy. Why it is magnetic energy? Here the magnetic field across the inductor starts, isn't it? So, the magnetic field starts changing. So, it is the magnetic energy. So, magnetic energy from 0, it starts increasing. So, what happened to here across the capacitor? Across this capacitor, here energy increases and here the energy decreases because the Q0 component decreases then, isn't it? The charges starts flowing. So, the amount of charge stored in the capacitor, it decreases. Same way, what happened? Here the magnetic energy, that is the energy stored across the inductor, increases, and how is it? It is equal to half L I square for the time being. And what happened? After some times, this capacitor is completely discharged. Capacitor will become completely discharged, and what happened to the charge here at that time? Q becomes 0. So, what is the energy across the capacitor at that time? After some time, here we can take the initial time t is equal to 0, and here the time becomes t is equal to t1. So, it is completely discharged. So, the electrical energy becomes 0, and what happened to the charge? That charge is converted in the form of current. Charge starts flowing. So, that will be changed to current. So, across the inductor, there will be the maximum magnetic energy, that is half L I0 square, where I0 is the maximum amount of current flows through the inductor. Okay, so initially what is this? UE is equal to half Q square by C. At that time, what is the energy across the inductor? No current. So, the energy across the inductor is 0. Then after sometimes what happened? This capacitor charge starts discharge to the inductor. Isn't it? Discharge to the inductor. So, the amount of charge stored in the capacitor decreases. Meanwhile, what happened? The current through the inductor increases. Okay. So, this is the case. It comes in between. Okay. That is, here we can write it is equal to UE is equal to half Q square by C, where Q is the amount of charge at an instant of time. So, it is half Li square. Then after sometimes what happened? It is completely discharged. That is, Q becomes 0 here. So, the energy becomes 0 across the capacitor and the energy becomes maximum across the inductor. So, what is happening here? Here the electrical energy is converted to magnetic energy. Okay. Now, the electric energy is completely converted into magnetic energy. Then what happened? Is this condition will continue? No, it won't continue. Okay. So, from here this current comes and the capacitor again starts charging. the discharged capacitor starts charging, and how it will be? It will be in the opposite manner. Opposite manner in the sense the polarity of the capacitor will be changed. Okay, that is the direction of the current will be different. So this plate becomes negative and this plate becomes positive. So from the inductor the current reaches here and it starts charging the capacitor with the opposite polarity. So what happened? At that time Q starts increasing. Like the amount of charge across the capacitor increases. Meanwhile, the current across the inductor decreases. So after some times what happened? Here UE becomes is equal to half Q0 square by C and UB equal to 0. Current becomes 0. So for that time being, what is it? Now the capacitor is fully charged. The current charge becomes Q0. At that time, what is the current across the inductor? Current across the inductor becomes 0 and this magnetic energy becomes 0. So it changes alternatively. Initially, electric energy is maximum, magnetic energy is minimum. Then what happened? Electric energy becomes minimum, magnetic energy becomes maximum. Then again what happened? Electric energy maximum, magnetic energy minimum. So there is a variation in the electric energy and magnetic energy. Okay, so this continues. So this variation in this electric energy and magnetic energy, it is coming out in the form of an oscillation. We are calling it as the oscillation or it is the wave, and such waves are known as the electromagnetic wave, EM waves. And what is this? Electromagnetic waves. Electromagnetic waves, that is conversion of what? Electric energy to magnetic energy and magnetic energy to electric energy, vice versa. It continues. So that oscillation, that variation in energy, we are getting it as the electromagnetic wave. And what is the frequency of the this wave? The frequency will be equal to 1 by root LC. Okay, 1 by root LC. And we are seeing this. What is this? We studied this as the resonant frequency. Omega is equal to 1 by root LC, or F is equal to 1 by 2 pi root LC. And from this, substituting the value of L and C, we are getting the velocity of light. Isn't it? Velocity of light as 3 into 10 raised to 8 meter per second using this relation. So from this, the relation between the electromagnetic waves with the electric field and magnetic field comes. It is called the LC oscillation. So this is the qualitative study of this production of the LC oscillation. So it continues. Okay. So this step by step. Now the next diagram, what is it? It goes in the opposite. This now the completely charged capacitor we will get. So what happened? The capacitor starts discharging. So what at that time, this electrical energy will change to magnetic energy. Okay. Then again that becomes 0, magnetic energy becomes 0, electrical energy becomes maximum, and so on. Okay. So that is the LC oscillation. Write down next question. Explain qualitatively how LC oscillations are produced. Explain qualitatively how LC oscillations are produced. Okay. How LC oscillations are produced. Then we have to see whether it is damped oscillation or undamped oscillation. Here we are considering this inductor with a zero resistance. Okay. So in such cases, we can say that these oscillations are undamped oscillation. What is that? Undamped oscillation, always the frequency or the amplitude remains constant. Such oscillations are known as the undamped oscillation. But practically what is said, this is LC oscillations are damped oscillation. Why? Here we are considering this inductor with a negligible resistance, but practically it is not possible. So some resistance will be there for the inductor. So what happened? The resistance is there. The energy loss will be there in the form of heat. Okay, in the form of heat. And if the resistance is too small, then also some radiations will be there. Energy will be radiated out, So practically this undamped oscillation, it is not possible. This LC oscillations are damped oscillation, and this LC oscillations are the basic working principle of this TV, radio or the devices. That is where we are using this electromagnetic radiations. Okay, so that is about the qualitative description. That is the variation of electric energy to magnetic energy and magnetic energy to electric energy. Next we go for the mathematical treatment. That is, we have to show that what is it, this is obeying that or following the equation of a wave equation we studied last year, isn't it? So this equation, mathematically the equation of this variation is equivalent to the expression for a wave. Okay, so consider this parallel combination of capacitor and inductor. Capacitor of capacitance E and inductor of inductance L is connected. Okay, so while discharging, what happened? The current starts flowing through this, and what is the current? We know current I is equal to minus dq by dt, and we know that when the current flows through this inductor, there will be an induced EMF. Okay, so induced EMF across the inductor, is minus L di by dt. We have already studied that, where L is the inductance and I is the, or di by dt is the rate of change of current. We have the equation. And what is the potential difference across the capacitor? Potential difference across the capacitor is equal to, if Q is the charge and say V is the potential difference, what is the relation? Q is equal to C. Yeah. So V is equal to Q by C. So potential difference across the capacitor is equal to Q by C. Then according to Kirchhoff's law, what is it? According to Kirchhoff's law, second law states that, this is the loop law, states that the applied potential difference and the potential drop across each component will be equal, or the net potential across the closed loop is equal to 0. That is the Kirchhoff's second law. So we can apply Kirchhoff's second law here. So we can write minus L di by dt is the potential drop across this. Okay, plus Q by C is equal to 0. Minus L di by dt plus Q by C is equal to 0. That is based on Kirchhoff's second law. Okay. And here, just a modification. We know I is equal to dq by dt, isn't it? I equal to dq by dt. So here, d by dt of I, that is d by dt of dq by dt. That is, we are changing the equation in terms of q. Okay, I and q relation we know. So we are changing this equation in terms of q. So what is it? It is d square q by dt square. That is the second order differential equation. So substituting that, what will you get? It is equal to minus L d square q by dt square plus q by c is equal to 0. Instead of I, you have written it as minus L d square q by dt square plus q by c is equal to 0. So here, that minus I is equal to minus dq by dt, so thus minus comes, this comes plus. Okay, so minus L dq by dt d square q by dt square plus q by c is equal to 0. And I am writing here, I am taking this L, I am removing this L from this. So what will you get? D square q by dt square plus q by LC. I am dividing this equation by L. So q by LC is equal to 0. D square q by dt square plus 1 by LC into q. 1 by LC into q equal to 0. And what is that? 1 by LC is a constant. So we can write the equation as d square q by dt square plus, I am taking this as omega square, q is equal to 0. omega square is equal to 1 by LC. Okay, we have seen that omega is equal to 1 by root LC. So here omega square, instead of 1 by LC, I am writing it as omega square. So d square q by dt square plus omega square q is equal to 0. And what is this? This is equivalent to a expression for the simple harmonic motion, that is d square x by dt square plus omega square x is equal to 0, where omega is the angular frequency there. So what is it here? What the variation in the energy or conversion of energy from electrical energy to magnetic energy, it is coming out in the form of oscillation. Okay, that is equivalent to a simple harmonic motion. So that's qualitatively we have seen that the variation in the energy, and we just said that it is coming out of a wave, as a wave or as an oscillation. And here the output is in the form of this second order linear equation, and it is proved that it is coming out of an oscillation in the form of an oscillation. Okay, then we have to prove this, how the variation comes. Okay, so what is it here? Just we are applying the Kirchhoff's law and just modifying, and we are getting the linear equation, second order linear equation. So we got the solution of the representation as in the form of the linear differential equation of second order. Okay, second order linear differential equation, that is half q square by dt square plus plus 1 by LC q is equal to 0, or LC we are represent it as omega square. So this is the expression for the simple harmonic motion, which is having the solution, that is q is equal to a cos omega t plus b sin omega t. You remember that d square x by dt square plus omega square x is equal to 0, and x is equal to a cos omega t plus b sin omega t. Oscillation and waves +1 chapter. Then we can solve this and we can prove that what we have explained, we can prove mathematically. So consider the initial time. That is, initial time the capacitor is fully charged and t is equal to 0. What is q? Q is equal to q0. The capacitor is fully charged, so the maximum charge is q0. So apply the condition here. At t is equal to 0, q becomes q0 is equal to a cos omega into 0 plus b sin omega into 0. So omega into 0, 0, sin 0 is 0 and cos 0 is 1. So E is equal to Q0. Okay, so the first term, this maximum amplitude first term Q0 is equal to A, we will get. Okay, so that is the charge. What is the current? We know current I is equal to dq by dt. Isn't it? The current will be dq by dt. So differentiate this equation 1. That is d by dt of what is q? A cos omega t plus b sin omega t. Okay. Two terms we can consider. So we differentiating first term, that is a omega sin omega t plus b omega, that is a cos omega t. Okay, a omega sin omega t plus b omega cos omega t. Okay, so we got differentiating this minus omega a sin omega t plus omega b cos omega t. What is it? It is equal to dq by dt. That is the current. So the same condition we are applying. That's initially what is the current we have to find out. What is the charge? We know that is q is equal to q0. So at t equal to t0, what is the charge? Q equal to q0. That is the maximum value. So what will be this LHS dq by dt? This is a constant value. So LHS will be 0. And what is the RHS? Minus omega a sin omega into 0 plus omega b cos omega into 0. T is 0. Okay. So what happened to the first term? The first term will be 0. Isn't it? Sin 0 is 0 and only we have the second term, that is omega b cos 0 is 1. Okay, that is omega b is 0, omega is not 0, so we can write b equal to 0. Okay, that is the second term, that is the sine term will be equal to 0. So what is it? Initially we are getting what? At the time t is equal to 0, there is a charge, that is q0 will be there, but the current, what is the current? The current is becoming 0, isn't it? At the first time, initial time t equal to 0. So we can write the equation as, what is it? q0 is equal to what happened to the b term? B term is equal to 0, and we are getting a term is equal to q0. So we can rewrite the equation as, substituting the values of constant, we are getting q is equal to q0 cos omega t, q equal to q0 cos omega t, because the second constant is becoming 0, then b is equal to 0 we are getting. And what is I? I is equal to dq by dt. So what is it? d by dt of q0 cos omega t, that is q0 omega sin omega t, q0 omega sin omega t minus. Okay, so substituting the value of t here. Okay, one is charge is in terms of force and current is in terms of sign, that is electrical energy, and this is the magnetic energy. So as time changes, time t equal to 0 here, what is it? There is maximum charge. T equal to 0, what happened to the current? This term becomes 0, the current becomes 0. Okay, then the t changes, what happened to the force value? It decreases, accordingly the charge decreases, and here the current increases. Okay, so it is moving with a phase difference, what we studied in the last session. So here this charge and current. So current maximum, charge minimum. Charge maximum, current minimum. That is maximum electrical energy, magnetic energy will be less. Maximum magnetic energy, electrical energy will be more. So what we explained, that is the qualitative explanation, that is proved that how mathematically also. Okay, q equal to q0 cos omega t, and the current will be q0 omega sin omega t. Understood? So this LC oscillation, the mathematical explanation for this LC oscillation. So the current and what is the frequency? Frequency is omega. Okay, so the variation is with the electrical energy and magnetic energy variation, it is with the frequency, and the frequency is 1 by root LC. Omega is equal to 1 by root LC, and the linear frequency we can write it is 1 by 2 pi root LC, because omega is equal to 2 pi f. Okay, so f is equal to 1 by 2 pi root LC. Okay, so that is called the LC oscillation, that is the electromagnetic production of electromagnetic wave. So write down next question. Next question. Show that when a capacitor is discharged, through an inductor, of negligible resistance, the discharge is oscillatory, and simple harmonic. Calculate its frequency, that is omega 2 pi f. Okay, f is equal to 1 by 2 pi root LC. So that is about the mathematical explanation for this LC oscillation. Next we have to see how this LC oscillation and mechanical oscillation. That is this wave, electromagnetic wave, how is it related with the mechanical wave? Okay, mechanical wave we studied last year. That is, if you are considering a spring and one end of the spring is fixed and a block is connected to the other end, it starts oscillating, isn't it? If you are applying an external force, it starts oscillating, and that oscillation is simple harmonic that we studied last year. So we have to compare this electromagnetic waves and that mechanical waves. They are simple harmonic. So here in LC oscillation, what is it? It is the conversion of electrical energy to magnetic energy and magnetic energy to electric energy. That is a vice versa. Okay. And in what is that? Mass spring system. What is it? You remember that here is the fixed end and this is the spring and a rod of mass M is connected, and we are applying the force. External force is applied. We know that a restoring force will be developed inside the spring. So there is a displacement in that direction, and the restoring force bring it back to the initial portion, isn't it? And there is a compression. So compression and elongation of the spring. So that makes the body oscillate, and we studied that that is a simple harmonic motion. And here, what is it? So what is the variation? That is the energy variation from kinetic potential energy to kinetic energy and kinetic energy to potential energy. Isn't it? Energy changes from kinetic energy to potential and potential energy to kinetic. And here what is it? Energy conversion from electric energy to magnetic energy and magnetic energy to electric energy. Okay, so we have the equation in that what is that? Mass spring system, and in this LC oscillator we derive the equation, that is d square q by dt square is plus omega square q equal to 0. And what is the expression we got in the mass spring system? That is d square x by dt square plus omega square x is equal to 0. Okay, omega square x is equal to 0. Here is the displacement, and here the variation in the displacement, change in the displacement, and here the change in the charge. This is for LC oscillation and this is for the mass spring system. So from the equation, comparing both the equation itself, it is in the same form, isn't it? It is a differential equation of second order differential equation. So following all these things, only the variable is different. Here it is q and here it is x. That is here the variation of the charge and here the variation of displacement. Okay, so we can compare this equation. So here the equation, d square q by dt square plus omega square q is equal to 0. That is for our LC oscillation, the system inductor and capacitor, and this is the case of the mass spring system. There it is the mechanical wave, and here omega is equal to 1 by root LC, and here omega is equal to root k by m, where k is the spring constant, isn't it? Where k is known as the spring constant and m is the mass of the body. And here the comparison is, here the inductance, that is inductance of the inductor, is equivalent to the inertial mass. That is a body of mass m is connected and we are pulling it, we are applying the external force, and there is a restoring force is developed in that. So the inductance analog, mechanical analog to the inductance, it is mass. And what is it? The capacitor connected in the LC oscillator, it is equivalent to the spring connected in the mass spring system. So here we can prove that for the mechanical system we require a force, that is the external force which we are applying, and an equivalent restoring force is developed. And what is the force? Force F is equal to ma. And what is A? A is equal to dv by dt, rate of change of velocity. And B we know, V is equal to dx by dt. So substituting for V, we will get it as m into d square x by dt square. Okay, m into d square x by dt square. And here, similar to this, in our LC oscillator, what is it? There is an induced EMF across the inductor, isn't it? When capacitor start discharging, current starts flowing, and we know that there will be an opposing EMF, back EMF will produce in the inductor, and that induced EMF is equal to minus L di by dt. That is acting as the inertial force or the restoring force in the case of an LC oscillator comparing with the mass spring system. Okay, and here what is it? I, we know I is equal to, yes, I is equal to dq by dt. Substituting instead of I dq by dt, what is it? Minus L d square q by dt square. So compare these two equations. Here m into d square x by dt square. Here which one is varying? Last I explained. Here the variable is x, that is displacement. And here what is the variable? The variable is charge. Charge is increasing from minimum to maximum. So same formula we are getting, same relation we are getting. So comparing this equation, here m and here it is L. So what is it? Here the inertial mass, where in the mass spring system we are having the mass of the body, and here in this LC oscillator we are having the inductance of the inductor. We are having the inductance of the inductor. And comparing with this equation, here omega is equal to 1 by root LC and omega is equal to root K by M. So the equivalent to this spring constant K, what is it? It is 1 by C. Spring constant, it is 1 by C, isn't it? So here the spring constant, that is K, determines required to produce the unit displacement. We know that, isn't it? The force, that is a constant, F proportional to minus x and F is equal to minus kx, and that proportionality constant is known as the spring constant. So this determines the displacement when we are applying the force. Similarly, here what is it? Here the capacitance determines what is that? The flow of charge. Why? That is, we know that Q is equal to CV and C is equal to Q by V, or 1 by C is equal to V by Q. So comparing with that, it is equal to 1 by C is equal to V by Q. That is the potential difference. Here, what is it? The spring constant, and here it is the potential difference. That is the opposition. Okay, opposition to the flow of charge or current, it is what? This capacitance. And here the displacement, the mechanical wave, what is it? The displacement is determined by the spring constant. Similarly, here the oscillation, it's the electrical wave, that is the electromagnetic wave, it depends upon the capacitance of the capacitor which we are using. Okay, that is how much charge is flowing. Accordingly, what is it? The conversion occur from electrical energy to magnetic energy. Okay, so when a spring oscillates, what is it? Kinetic energy is converted to potential energy, and potential energy is converted to kinetic energy. You remember that graph? We are getting the maximum kinetic energy, potential energy graph. So same way, what is it? This LC oscillation also, it is similar to the mechanical wave. That is, the LC oscillation is similar to the mechanical oscillation, or electromagnetic wave. It is similar to the mechanical wave. Okay, so here what is it? Instead of this mass which we are using, we are having the inductance, and instead of this spring constant, we are having the reciprocal of capacitance. Okay, so LC oscillation, qualitatively, how can we explain that? It is just the variation of electrical energy to magnetic energy and magnetic energy to electrical energy, that is charging, discharging of the capacitor. Okay, and mathematically we proved that oscillation is coming out in the form of sine wave. It is that oscillation is a simple harmonic, because we are getting the equation, solving the equation, we are getting this d square q by dt square plus omega square q is equal to 0. That is satisfying this general expression for this simple harmonic wave, and it is similar to a mechanical wave also. Okay, it is similar to a mechanical wave also. So write down the next question. Explain, explain the mechanical analogy of, explain the mechanical analogy of LC oscillation. Mechanical analogy of LC oscillation. So here we are having the things what we discussed, that's analogies between mechanical and electrical oscillation. So this is the mechanical system, that is the mass spring system, and this is our LC oscillator. So here for we are having mass, and in electrical system we are having the inductance, and here the displacement, isn't it? Displacement of the body, and here the charge. Okay, unit flow of unit charge. Charge is moving. And here velocity is dx by dt, and here it is the current dq by dt, and force constant is k. Similar to that, here the reciprocal capacitance 1 by c, and here what is the energy? Half kx square plus half mv square, potential energy plus kinetic energy, and here electrical energy plus magnetic energy, half q square by c plus half li square. It is there in your textbook. So this diagram also you draw in your. Okay, let us move to the last topic of this chapter, that is transformer. Transformer. So in the last chapter we studied one device, that is AC generator. How can we generate AC? That is the alternating current. Now we are going to discuss about the transformer. That is transform. It's a device which we are using to transform. What is that? Transform the resistance. Okay, or transform the voltage. That is a transformer. Okay, so what is a transformer? Transformer is a device which we are using to convert low voltage at high current to high voltage at a low current. Okay, that is simply we can say either you can increase the voltage by using the transformer, or we can decrease the voltage by using the transformer. Okay, you have seen the transformer. Near to your junction there will be a transformer. Then in small this electric devices, that is radio, TV and all, there is a transformer. In our school there is a transformer. So in the power station there is a transformer. Okay, so what is said? It is this transformer we are using to change the voltage, either to increase the voltage or to decrease the voltage. Okay, so transformer is a device which we are using to convert, what is it, low voltage at a high current to high voltage at low current, or vice versa. Okay, and what is the working principle of this transformer? Working principle of the transformer is nothing but it is our mutual induction. It is mutual induction. So we know what is mutual induction. What is mutual induction? There are two coils, and whenever the flux associated with the primary coil changes, an EMF will be induced in the secondary coil, isn't it? So same thing. But here in the transformer, what will be the construction? There are two coils, isn't it? Mutual induction, definitely there will be two coils. So one coil is the primary coil and the other one is the secondary coil. So what is transformer and what is the working principle of transformer? Next we will discuss about the construction. Okay, so mainly there are two types of transformer. One is core type transformer and shell type transformer. So nowadays this core type transformer is using, and inside the electric devices, radio, TV and all, it is shell type transformer. So what is this core type and shell type? So we know there are two coils, isn't it? There are two coils in the transformer. So in core type, the two coils are wound like this. Here, both sides, lot of coils will be there. First coil will be wound here and the second coil will be wound here. Okay, and in shell type, here, first coil and second coil will be wound one over the other. Okay, so two transformers, two type of transformers, shell and core. And these two coils, this first coil it is known as the primary, and the second coil is known as the secondary. Here this is the primary and this is the secondary. Okay, so the input will be given across this primary and output will be taken across the secondary. We will give the input to the primary and output we will get the secondary. And according to the action, we will move to this type of transformer. According to the action, there are two types of transformers. Like this. Here you can see the difference, isn't it? What is the difference? Yes, the difference in the number of turns, isn't it? Here in the primary 3 turns are there, in secondary only 2. That is, the number of turns of the coil in the primary is more than that of the number of turns in the secondary. And here number of turns in the primary is less and number of turns of the coil in the secondary is more. And it is wound over a metallic frame. Okay, it is the insulate that is laminated iron core, that is to reduce the flux leakage, that is to reduce the inductance. Okay, it is the laminated core, that is one sheet one over the other, it is arranged and it is making as a metallic block, and over that this windings are doing. Okay, copper windings, metallic windings are. So here difference, here we can take N1 is the number of turns in primary and here also N1 is the number of turns, and secondary it is N2 and here also N2, or take this as NP for primary and NS for secondary. And here what is the condition? Here NP is greater than NS and here NS is greater than NP. So such transformers where the number of coils are more, accordingly this transformer is known as a step down transformer and this is a step up transformer. Step down transformer and a step up transformer. So transformers are of two types, step down and step up. So the main difference is in the number of turns of the coil in the primary and secondary. And what is the function? Step down transformer decreases the input voltage. Step down transformer decreases the input voltage and step up voltage transformer increases the input voltage. That is, suppose here we are giving 230 volt here in the primary, and this is step down transformer, we can make it as 110 volt or lesser than that. That's according to the number of turns. And here what is it? If 110 volt we are giving, we can make it as 230 volt here. Okay. So step up increasing voltage and step down it is decreasing the voltage. Okay. So by construction there are two types, and according to the use again there are two types. What is that? Step down and step up transformer. Okay. So what is a transformer? It is a device which can convert low voltage at high current to high voltage at low current and vice versa. And what is its working principle? Working principle is mutual induction. And how many types of transformers are there? There are two types of transformers, step down transformer and step up transformer. And what is the difference? In step down, number of turns in the secondary is less than that of the number of turns in primary, and step up, number of turns in secondary is more than that of number of turns in primary. Next we have to see the work. Okay, so here it is connected across an AC source, that is primary is connected across an AC source, and we know that when current flows there will be flux produced, isn't it? So we can take 5P is the flux produced across the turns in the primary, across the primary. Okay, and we are considering that this is an ideal transformer. We are assuming that this is an ideal transformer. What is an ideal transformer? Ideal transformer means there is no flux leakage. So whatever be the flux produced here will be transferred to the secondary. Okay, there is no flux leakage in between. So based on that assumption, we are going for the derivation. So there is no flux leakage. So here phi p is the flux produced in the primary, and we can take phi s is the flux in the secondary. And according to that, we know that the EMF induced in the primary is EP is equal to, what is the expression? E is equal to minus d phi by dt, isn't it? Minus d phi by dt. So EP is equal to minus d phi p by dt, and NP is the total number of turns in the coil. So we can write it as minus NP d phi p by dt, and ES is equal to, ES is the EMF induced in the second. So ES is the flux produced in the second, induced EMF in the second, isn't it? If phi s is the flux in the secondary, what is it? Minus ns d phi s divided by dt. Take this as equation 1 and this as equation 2. And I told you we are deriving on the basis of one assumption, that there is no flux leakage. So what is it? Phi p and phi s are equal. So we can divide this equation 1 and 2, and we are going for the ratio, that is equation 1 by 2. What will you get? EP divided by ES is equal to minus NP d phi p divided by dt divided by minus ns d phi s divided by dt. This phi s and phi p are equal. Phi s is equal to phi p. What happened? These two terms get cancelled. So what is the relation? EP divided by ES is equal to NP divided by NS. EP divided by ES is equal to NP divided by NS. So as the number of turns changes, isn't it? So we can write the equation for the EMF or the voltage in the secondary. What is it? ES is equal to EP NS divided by NP. Isn't it? NS divided by NP. So according to the number of turns in primary and secondary, if this is more, what happened? ES will be more. If it is less, ES will be less. Accordingly, we are having the step up and the step down transformer. And this ratio, it is known as the transformation ratio. It is known as the transformation ratio. Okay, so that ratio decides whether it is a step up, it is a step up transformer or a step down transformer. It is known as the transformation ratio. Okay, so what is it? Just considering the number of turns and flux, and we are using this equation, we are getting EP by ES is equal to NP by N. Next we have to see what is the current in the primary and the secondary. Current in the primary and the secondary. So here the transformer is an ideal transformer. So what is it? The output power and input power will be same. No energy loss. So what is the power in the primary or in the input region? The same power we will be getting as the output power. So we can take IP is the current in the primary and IS is the current in the secondary. So we know the power, input power is equal to EP IP. Isn't it? VI, power P is equal to VI. So here it is EP and IP in the primary. That will be equal to ES into IS. Right? Voltage across the secondary and the current across the secondary. So write the ratio ES divided by EP is equal to IP by IS. It is IP by IS. It is just opposite. Isn't it? So what is it? As the voltage increases, current decreases. Current voltage decreases, current increases. So here we can add this is equal to IP by S. ES divided by EP is equal to NS divided by NP is equal to IP by IS. So here we are taking the case of ideal device, that is input power. Input power is equal to output power. Okay. output power. So ES by EP is equal to NS by NP is equal to IP by IS. Okay. And what is the efficiency of this? Any device, we have to go for the efficiency. What do you mean by the efficiency of the device? Efficiency is the ratio between output power to input power. It is the ratio, that is the efficiency. Efficiency is represented by the letter eta. The last year in heat engine you studied efficiency. Efficiency is the ratio between the output power to input power. And we know that practically it is not possible. What is that? A 100% efficient device. Okay, so here we are for deriving this condition, we are considering this transformer is an ideal one, that is with a 100% efficiency. There will be energy loss. So next we have to see what are the energy losses in the transformer. There's a different different types of losses are there. One is the copper loss. What is that copper loss? We know that that's a coil. It is made up of copper and a metallic frame we are using. So here there is a possibility of energy loss in the form of heat. Okay, that is, we know that when you are standing near to the transformer, we feel a little bit temperature there, hotness there. That is because of the energy loss. That causes, proves that there is an energy loss in the transformer. That is the heat produced. Okay, it is having high resistance and current flows. So energy loss in the form of heat. Then eddy current loss. What is that eddy current? It is the current produced because of the change in the flux associated with a metallic frame. So here we are using the frame, isn't it? And the coils are wound over that metallic sheet. So there is a magnetization. It's alternating current flows. There is a flux change. So the magnetic flux change will be there. That produces eddy current. So that eddy current loss will be there. So the flux is lost in the form of eddy current. And there is flux leakage. So what is that flux leakage? From the primary, the flux have to reach there in the secondary, isn't it? So in between, that converted as the eddy current, or there will be heat, all these things come, that is the flux leakage. And one more thing is there, that is the hysteresis loss. Hysteresis loss. What is that hysteresis loss? When the current flows through the metals, there is a magnetization and a demagnetization occur. So because of the magnetization property, what is that? There is an energy loss, that is known as the hysteresis, and there is a energy loss in the case of transformer in the form of hysteresis loss. So these are the some of the energy loss in the transformer. They are copper loss, eddy current loss, flux leakage, and hysteresis loss. Okay, so write down the next question. What is a transformer? What is a transformer? What is its working principle? With the help of a diagram, explain its working. Derive the transformation ratio. Derive its transformation ratio. Expression for current and power. Next question. What are the energy losses in the transformer? What are the different types of energy losses in the transformer? The next question. What are the uses of transformer? Okay, so that's all in this chapter. Complete the homework and submit to me. Okay, thank you.